So now that we've sharpened our focus on the history and current views of this disease process of dental caries, and we've discovered that it's a dynamic process. It's a balance between pathologic factors and protective factors, as Featherstone pointed out. And we've done our due diligence covering the pathologic factors. Let's try to focus some attention on protective factors in the equation. The following table describes the function of saliva-derived components in the dental biofilms. And as you can see in the right-hand column, the protective functions of saliva are plentiful. They aid in remineralization, acid buffering, digestion, lubrication, aggregation and clearance of microorganisms, antibacterial agent, antifungal and antiviral agents, bolus formation, and taste. We could dedicate much time and resources to the study and understanding of all of the roles that saliva plays in our mouth and throughout our body. But this table does a great job of succinctly describing some of the main functions of saliva. Saliva is produced by the parotid, the sublingual, and the submandibular gland. The glands produce and secrete these serous or mucus secretions into the oral cavity in various locations. And the secretions of these glands are affected by many medications, which are commonly taken by children and adults. Additionally, other diseases can affect the production and secretion of salivary glands. Saliva is a clear fluid, and it's very interesting. It's a colloid, and I think it would be helpful to review the principles of colloidal formation before we move on. And I think it's timely to review the principles of colloidal formation and apply these principles to saliva before we move on.
And water can also mix with large charged molecules, large polar molecules like proteins, okay? Remember at the kind of towards the beginning of the first lecture, I talked a little bit about colloids, okay? Colloidal solutions. Okay, remember all a colloid is basically, think of a colloid as a protein mixed in water. I mean, remember Jello, okay? So if I take this big protein and stick it in water, these smaller waters are going to kind of stick inside the coils of here, okay, of this protein, and then as a result, but there's still going to be a little bit of water kind of found around the protein, all right? So as a result, you're going to form a gel, not exactly a solid, not exactly a liquid, okay? And what's nice about these colloids or these sticky these gels is that they're relatively sticky, okay, which means we're talking about connective tissue here. Okay, so we form a very diverse type of tissue inside of our body by mixing proteins in water. All right, and then as I mentioned earlier, being that water can mix so well with so many, being that it is the universal solvent, it would make sense that it's our main transport medium as well, i.e., blood. Okay, just remember, you guys know that lipids and water, that they don't mix. Okay, because, fats are non-polar, they're non-charged, water is polar, okay, nothing to gain from one another. So they do not mix with one another. But the beauty of this is we can still circulate, because remember, there are certain hormones, like for example, steroid hormones are made out of fat. Okay, they're derived from cholesterol. Okay, so how do we circulate? So then how do we circulate a fat-based hormone around our watery blood? Well, we can get around that we can stick this fat to a protein, the proteins can mix in the water, and then we can circulate that fat hormone around the body while it's stuck to what we call a carrier protein. So that's the nice thing about water being so universal in its solvency, is that we can transport essentially anything throughout our system. Even if it doesn't directly mix with water, we can still stick it to a molecule that does and circulate it around the body. So that's the beauty of water, as being a universal solvent.
So a couple of questions after viewing this video would be, is saliva a connective tissue? So we can see that saliva is a diverse tissue fluid. It's composed of proteins and electrolytes, all of which have a specific function within our body. This is a representation of what proteins and electrolytes look like when they're put together like in saliva. You have an ionic liquid, polymer, and a cross-linker at times. Many components of saliva, which are secreted, can interact with the tooth surface in the biofilm or perform a specific function outside of the biofilm. Saliva is composed of precipitated salivary glycoproteins, enzymes, and immunoglobulins. Proline-rich proteins are significant components of the serous secretions of saliva. They maintain saturation by keeping calcium and phosphate in solution. They help remineralize. They bind to calcium fluoride for extended release. In the organic composition, there are a number of proteins and glycoproteins in human saliva that may influence several aspects of oral health. Many of these proteins contain high levels of proline and are therefore designated proline-rich proteins, which comprise almost 70% of the total protein content of human parotid saliva. Since amylase comprises most of the remainder of the total protein content of parotid saliva, the other proteins, such as lysozyme, lactoferrin, peroxidase, and secretory IgA, are in fact relatively minor components. Statherin allows saliva to maintain its state of supersaturation with respect to calcium and phosphate salts. Thus, these protein components contribute greatly to the maintenance of an intact dentition through their binding and inhibition of spontaneous calcium phosphate precipitation and crystal growth, while at the same time providing possibilities for heterogeneities and microbial colonization through their specific bacterial binding patterns. So without going into too much detail, I would like us to gain an appreciation for this connective tissue fluid, this colloidal fluid that we call saliva, and really become aware of the nature of the proteins and the enzymes and the immunoglobulins that are secreted in this fluid. Not all bacteria are bad for us. Certain bacteria in dental biofilms may lessen the effect of cariogenic or acid-producing bacteria. For example, Veillonella metabolizes lactic acid produced by acidogenic bacteria. Again, recall that our two major cavity-causing bacteria, Streptococcus mutans and Lactobacillus, are homofermentative, meaning that the byproducts of metabolism for both of these bacteria is mainly lactic acid, which, if you recall, deprotonates 10 times as easily as acetic acid does. Streptococcus salivarius and Streptococcus sanguinis produce arginine deaminase and urease that create urea and ammonia compounds, which raise the dental biofilm pH, acting like a buffer. In addition to non-cariogenic bacteria, studies have shown the benefits of many species of probiotics, which may ultimately affect the flora of our oral cavity. Again, recall the benefits of the acquired enamel pellicle, a very thin pellicle which contains key salivary proteins, slatherin and PRP, which are intimately associated with crystallization and post-eruption maturation. With the availability of calcium, phosphate, and fluoride from saliva in the dental biofilm, fluoride becomes incorporated into hydroxyapatite by means of absorption of fluoride into pre-existing hydroxyapatite crystal. Fluoride exchanged for hydroxyl groups in hydroxyapatite and new crystal growth of fluoridated hydroxyapatite from fluoridated mineral phases. With post-eruption maturation, the porosity and permeability of the enamel is reduced substantially, all a benefit of the acquired enamel pellicle during post-eruption maturation. And I feel it's remarkable to comment that these key proteins can be incorporated into our biofilm even after the tooth has erupted. Components of the saliva can act as buffers to protect proteins, enzymes, and immunoglobulins in the saliva from becoming denatured and losing their function. Bicarbonate, phosphate, carbonic anhydrate, silane, basic alkaline proteins, and urease aid the saliva in buffering. Recall that with denaturation of a protein, the solubility of that protein goes down significantly, and the protein loses its function. The pH of the saliva is highest in the morning and decreases after eating when starches and sugars are metabolized to acid by cariogenic bacteria. So now that we have an understanding for some of the protective factors in the oral cavity, which are helping us fight this war in this tiny little tissue space between the biofilm and the surface of the enamel, let's focus on the enamel and how it dissolves and precipitates or remineralizes. The solubility product, or KSP, is the equilibrium constant for a chemical reaction in which a solid ionic compound like hydroxyapatite or fluorohydroxyapatite dissolves to yield its ions in solution. If the solution is not saturated with ions, no precipitate will form. In this case, the product is called the ion product, or QSP. A solubility equilibrium exists when a chemical compound in the solid state is in chemical equilibrium with a solution of that compound. The equilibrium is an example of dynamic equilibrium, in that some individual molecules migrate between the solid and solution phases such that the rates of dissolution and precipitation are equal to one another. When equilibrium is established, the solution is said to be saturated. The concentration of the solute in a saturated solution is known as the solubility. Units of solubility may be molar or expressed as mass per unit volume, such as micrograms per milliliter. Solubility is temperature dependent. A solution containing a higher concentration of solute than the solubility is said to be supersaturated. A supersaturated solution may be induced to come to equilibrium by the addition of a seed, which may be a tiny crystal of the solute or a tiny solid particle which initiates precipitation. In any aqueous ambience with a neutral pH, the hydroxyapatite crystal dissolves minimally and releases the calcium, phosphate, and hydroxyl ions into the solution. If the solution, for instance, is the oral fluid that already contains the same minerals, it becomes supersaturated, resulting in the precipitation of the minerals back onto the tooth enamel in a dynamic equilibrium. Recall as well that some of the salivary proteins lie within the biofilm, and depending on their level of function within the biofilm, they may also be able to sequester some of these ions in solution as this equilibrium takes place. Thus it is evident that the dissolution of the hydroxyapatite crystal occurs at a certain acidic pH, which is referred as being below the critical pH of hydroxyapatite. The critical pH is the pH at which a solution is just saturated with respect to a particular mineral. For the hydroxyapatite crystal, it is approximately 5.5 to 6, below which the enamel disintegrates. Or rather, the equilibrium is pushed towards disintegration. Disintegration of enamel will supersaturate the oral fluid, this fluid between the biofilm and the surface of the tooth, with hydroxyapatite ions, calcium, phosphate, and hydroxide, which will be free to react accordingly. The chemical reactions of D and remineralization are also explained in relation of the ion activity product in the solution versus the KSP, the solubility product, constant of enamel. The IAP denotes the product of the activity of the ions released into the solution during dissolution and is expressed with regards to hydroxyapatite crystals as 10 calcium ions times 6 phosphate ions times 2 hydroxyl ions. The solution is said to be in equilibrium with hydroxyapatite when the ion product equals the KSP. Demineralization occurs when the IAP in the solution is less than the KSP, and remineralization occurs when the IAP in the solution is greater than the KSP. This chart explains this process clearly. At a neutral pH, we have the solubility product of hydroxyapatite crystals being the same as the ion product. Therefore, we have a saturated solution, which can yield formation of hydroxyapatite and fluorohydroxyapatite, depending on the ions which are found in solution. Under natural conditions and under an acidic environment, we have supersaturation of the oral fluid with the ions in the solubility product. Basically, this chart says that when the particular ions are in solution equivalent to the product of ions needed for formation of a crystal, then that crystal is free to form. When there are a greater number of ions in solution than the ions that are needed for the crystal to form, under neutral pH, the oral fluid will become supersaturated, and remineralization may take place, especially under more acidic conditions when more ions are available. This, of course, depends on the functionality of the proteins and the stores and types of minerals which are present in the solution, and the concentration hydrogen ions in solution. Of course, when there are very few ions available for crystal formation or remineralization, and we are subject to a lower pH, we can do nothing but demineralize our crystal under acidic conditions. Thus, the process of demineralization and remineralization is a dynamic process, with periods of demineralization interspersed with remineralization. The effects of demineralization can be reversed if there is adequate time between acidogenic challenges to allow for remineralization to occur. It is important to note that even though dental plaque and biofilm are saturated with calcium, phosphate, and fluoride, the rapid increase of hydrogen ions of more than 100-fold and potentially as much as 1,000-fold, depending on the change in pH caused by the type of food or beverages that are consumed or health conditions of the oral cavity. This change in hydrogen ions, this rapid increase in hydrogen ions, provide a strong driving force to diffuse hydrogen ions into the fluid in the pores surrounding hydroxyapatite crystals in sound surface and subsurface enamel. This process results in demineralization of the subsurface enamel by means of calcium and phosphate moving towards the enamel surface, which results in egress of calcium and phosphate from the subsurface enamel into the overlying biofilm. Again, this driving force is created by an increase in hydrogen ions of at least 100-fold and potentially 1,000-fold in plaque secondary to active fermentation of fermentable dietary carbohydrates. Because of the high calcium and phosphate content in the overlying pellicle and dental plaque, a certain amount of calcium and phosphate precipitates in the superficial layers of the affected surface enamel and helps retain an intact enamel surface layer, although deeper inside the lesion could be less mineralized. We see a key to deep remineralization being to maintain a porous enamel surface layer and a saturated KSP with ions key for remineralization, using the driving force of the ions to get deep within the body of the lesion of the cavity.